An alkene is a molecule that has a pi bond, which we draw right here as just a double bond. But if you think about what is happening in that pi bond, if we look at these two carbons specifically, I have a carbon and another carbon bound with a sigma or single bond. These are holding on just like a regular bond. But then we have the p orbital that sits above and below, like that, with the pi electrons just circling around. So they're hovering above and below the molecule, making that electron density concentrated much further away from the atoms. And the way I think of this is almost like walking a puppy on a long leash. So my in-laws have a mini schnauzer, and even though you hold the leash and you're walking along, that dog is just running circles and trying to trip you up and running in every which way, because with a long leash, she can get everywhere. And if you happen to bring something nearby with a positive charge, this puppy, these electrons that are so excited to just experience the world around it, will reach out and start leaning towards that positive charge, where if it's strong enough, it's going to break away. And that is how we get a lot of the different alkene reactions. So the common ones, the ones that you learn the mechanisms for, are called the electrophilic addition reactions. And that is because we're looking at an electrophile that's adding. So I wrote it here as an E+, but if I had to simplify or summarize all of alkene, or this category of alkene reactions, and really most of organic chemistry, let's keep that on the screen, it'll look something like this. I have a nucleophile, which I like to write as Nu with 2 electrons. The electrons remind me that it has either a lone pair or a negatively, it has a lone pair, but it can either be neutral or with a negative charge that wants to reach out for something. The nucleophile is negative or partially negative, and that means it will be attracted to an electrophile, something that is positive or partially positive. It'll use these 2 electrons to attack and make a bond. That is how we get a lot of the reactions that we're going to see with the electrophilic addition, with these alkene addition reactions. Before we go into the specifics, there's a couple more things that we have to look at, again, from the perspective of understanding rather than memorizing. And the first is the concept of syn versus anti-addition. We'll start with a very simple reaction. If I have an alkene that looks like this with a pi bond, and I react it with A and B, when the pi bond breaks, let's show plus because they're being added, I will get the molecule redrawn as I saw it, minus the pi bond. And then I have a new bond on the 2 carbon atoms that used to hold the pi bond. So the former sp2 carbon atoms, one holding the group A and one holding the group B. The way that these add are very specific to the reaction. Now in this molecule, you can't tell that there's a difference because I didn't give you stereochemistry, and therefore everything just looks flat. But if I show this on a ring, where the ring prevents the molecule from rotating, it locks all the bonds in place. If I do the same thing, where I add A and B across the pi bond, my product can be one of 2 different molecules. So let's draw 2 rings. I can show both A and B adding to the same side. In this case, I can draw them both coming out of the page on wedges or going into the page as dashes. So that will be randomly both coming out of the page. Or I can show one coming out of the page and then one going into the page, and I could have done the reverse. This is not random. This has to do with how the attack happens, and therefore it is really, really important that you understand this. When they add to the same face of the molecule, either both adding to the top or both adding to the bottom, this is called syn addition. Syn on the same side, they add together. And when one adds on top and one adds on the bottom, they add opposite sides. This is called anti-addition because they add anti to each other. This is not something that I want you to just blanket memorize. With each reaction, I'm going to show you why we have syn or anti based on the intermediates, based on how the reaction happens. And so that way you'll be able to reason your way to the answer rather than having it memorized. The next piece that I want to look at is Markovnikov's rule. Because Markovnikov has such a long name, I'm going to be calling this Mark's rule or writing it as Mark's rule for most of the session, just because it takes so long to write his name. Markovnikov's rule, a lot of students tend to memorize this as where the hydrogen goes. And technically, we do follow the path of the hydrogen when looking at Markovnikov's rule. And so if I give you an asymmetrical starting alkene, and I add a molecule that has, say, HX, where I place the substituents, where I place the incoming nucleophile is definitely important. It's not random. So I have two options here where I can put the hydrogen on the more substituted and the X on less substituted, or I can put X more substituted and hydrogen less substituted. When looking at Markovnikov's rule, we have to know why it's going to add in a specific direction. Now, a lot of students will memorize something like the hydrogen rich get hydrogen richer, a play on the rich get richer, or hydrogen goes to where there are more hydrogen atoms. And technically, that is correct. Let me show you why. In the starting molecule, the sp2 carbons, this one has no hydrogen, and this one has one hydrogen atom. And so the side that has the hydrogen got a second hydrogen. But if you memorize it that way, it's straight up memorization. It doesn't tell you what happened or why. And so I want to take a step back and I want to show you the mechanism, because anytime you have a carbocation intermediate, we're going to follow Markovnikov's rule based on the stability of the carbocation and nothing else. The nucleophile, just by the way, happens to follow. So let's look at the mechanism for this reaction, where I'm starting with an asymmetrical alkene. We already said that the pi bond has the electrons being very nucleophilic. They're sitting above and below the molecule. They're very excited. They want to reach out and grab. And so the way we'll show this is the pi electrons right here will reach for, we draw an arrow towards the hydrogen. Why specifically the hydrogen? Because if you think of HX, let's make it HCl for a hydrohalogenation mechanism. The chlorine, being a highly electronegative atom, is pulling electron density away from hydrogen, making it very partially positive. And the hydrogen, very partially negative. And the hydrogen becomes very partially positive because the nucleus is exposed. When that happens, the pi bond is attracted to the partially positive hydrogen. That is my electrophile. That is where the electrons are going to go. Hydrogen can only have one bond. And so when it is grabbed, it has to let go of the chlorine, give the chlorine back the electrons it's reaching for. And I have a choice now between two different intermediates. Let's move this over so we have room. My first intermediate has, actually, let me draw the skeleton for both. If I put the hydrogen on the more substituted carbon or the less substituted carbon, the other carbon gets nothing when the pi bond breaks, and that is why we get a carbocation. A carbocation is just a formal charge of +1. If you don't remember this concept, I have a formal charge shortcut video, which, make a note, I'll put it in the description. I'll link it into the video description. The formal charge just means that carbon is missing something. You break the pi bond, you don't replace it with anything else, it now has a positive charge. So which of the two is more likely to want to have the positive charge? That is the question you have to ask, and that is how you're going to understand what is happening here. We're looking at stability. Which one is more stable? When it comes to carbocation stability, the more substituted the carbocation, the more stable it is. And that means a comparison between a secondary carbocation and a tertiary carbocation Very simple. The tertiary is more stable, not the secondary. That is the one that forms. And by the way, in order to form the carbocation here, I need the hydrogen to get shoved out of the way, and it happens to go to the last substituted carbon. Let me see a heart in the comments if you follow about why it's not about the hydrogen, but rather about the carbocation stability that determines what happens here. And the rest of it just falls into place. I have a Cl- that is floating around the solution, the chlorine that broke off. The Cl- here is my nucleophile. And when that nucleophile recognizes a carbocation formed, it's attracted to the carbocation and immediately attacks the carbocation to finish the reaction. It doesn't care where that carbocation is. If there is a positive charge, it's going for the positive charge. So the slow step, the rate determining step, the one that will give us the ultimate positioning of where the nucleophile, the incoming nucleophile goes and where the hydrogen goes, has everything to do with the carbocation. And this is the logic behind Markovnikov's rule. And so here's how I want you to think of Markovnikov's rule moving forward. Markovnikov's rule ultimately tells us that if we have a carbocation intermediate, it forms on the most stable, meaning the most substituted carbon. And I'll show you how this works out in the reactions so that you'll have a lot easier time remembering which way to put your products. Do you follow Markovnikov's rule or anti-Markovnikov? With this in mind, if you haven't already subscribed to my channel, make sure you do so right away. And if you're just joining, welcome. If you're watching the recording, welcome. Let me know where you're watching from. For a copy of today's session notes, including my practice quiz and more, make sure you go to the pinned comment, which is aleaforsyth.com/orgolive. That is right there. Orgo Live, you'll get a copy of these session notes. Any other live stream that I've done, I'll send you those notes as well and additional practice material. The hydrogenation reaction. The hydrogenation is hydrogen right there in the word. That is adding hydrogen to an alkene. And to show you the regioselectivity, we'll use a ring. Hydrogenation is when I react an alkene with H2 gas, using some kind of metal catalyst, for example, platinum. What's happening here is not the pi bond reaching out, but it's actually a very different type of reaction where you probably don't have to know the mechanism, but I want to show it to you so that you understand what is happening. Let's say this right here is my metal catalyst, and it has a lot of hydrogen atoms that just got attached to it. Metal will grab onto hydrogen and hold on to it. If I bring that metal catalyst near my pi bond, the pi bond will be grabbed. So there's my alkene. The pi bond is grabbed. The chain is grabbed. The pi bond is broken. And now the metal is holding on to my alkene chain. I'll show the ring. Let's show the ring a little bit less shrunk. Here we go. The pi bond is right there. When the metal grabs it at the pi bond breaks. And now the metal is holding hydrogen and holding on to my carbon chain. Because the hydrogens are nearby, one of the hydrogen atoms will simply slide in and another hydrogen atom will simply slide in so that I wind up with something that looks like, this. Here is my ring, no longer attached to the metal because the hydrogen atoms took the place of where the metal was holding onto it. But because the metal was holding it and the hydrogens just kind of slid in, they wind up adding both down at the same exact position on the same side. And this is why we get a syn addition for hydrogen. You can show them either both coming out or both going in, but you have to show that it is syn addition. And because we have two hydrogen atoms, we don't have to worry about Markovnikov's rule, because that's typically when I have hydrogen and something else like a nucleophile. So this right here is very simple, and technically it doesn't matter how I drew the hydrogens because I just have more hydrogens back there. But one way that your professors will try to trick you with this right here is, instead of giving you hydrogen, they're going to give you a reaction that looks like this. Either starting with a molecule that has deuterium, or they'll have you react it with D2, and let's go with palladium carbide, just another type of metal that you can use. And now you do have to recognize that there is a hydrogen here and a hydrogen here. So when you do the reaction, the trick, first of all, to coming up with a product is to break the pi bond and recognizing that deuterium is simply a heavy hydrogen. It's an isotope of hydrogen that happens to have a higher mass, a mass of 2, dose. A lot of languages have the word for 2 that starts with a D. That's all it is hydrogen with a mass of 2. And then you choose to either put your hydrogens down or up. Now, in this case, it doesn't matter. But what if I go ahead and add a CH3? Now I don't have symmetry in the molecule, and I will have to show 2 different products because I most definitely can have the deuterium adding both up and down. So the methyl itself doesn't change. The methyl doesn't go up or down, but the hydrogen does. So on one, I show my hydrogens both going down. On the other ones, I show both of the hydrogens coming up. And then my incoming deuterium will be opposite. So here, I show both going up. And here, I show both going down, giving me 2 different products. What is the relationship between these 2 molecules? Are they A, the same exact thing? B, conformational isomers? Probably should use that here. Constitutional isomers? Are they enantiomers or diastereomers? A lot of professors will call these enantiomers, and that is absolutely incorrect. These are diastereomers. Actually, I don't know that you would have learned this concept yet. So if you haven't learned this, just completely ignore what I said here. If you have learned stereochemistry, what you're looking at is 1 chiral center the same and 2 chiral centers that are different. That is how we got the concept of diastereomers, but I'm not going to bring that up again because I'm guessing you probably have not yet learned alkene reactions. Stereochemistry this early. Maybe, I don't know. So let's just keep this to alkenes and keep going. So this is our hydrogenation. We're adding hydrogen. For the next reaction I want to look at is also one that starts with hydrogen, but this time it's a hydrogen and a halogen, so it's hydrohalogenation. What words do we have in here? We have hydrogen, H, halogen, X, chlorine, bromine, iodine. And typically you're not going to see this with iodine. You're going to see this with bromine and chlorine. And there are 2 types of hydrohalogenation reactions. The first one is probably the one that you cover here. The second one, many students will not learn until later. We'll start with an asymmetrical alkene so that we can focus on Markovnikov's rule. And we'll react it with, well, I already showed you HCl, so let's take a look at that again. And we'll put it specifically into a solvent that does not react. This is an inert solvent, which allows the focus to be on just the HCl. Recognize that this right here is a partially negative, therefore a partially positive. This is an electrophilic addition, which means we're going to have a carbocation intermediate. Now, I have videos that go through the individual mechanisms, but for the review, we're going to do the fast way, where if you're not asked for the mechanism, I want to make sure that you know how to approach this and how to get it. And so we recognize that we have a carbocation intermediate. The pi bond breaks. Where does the carbocation go? Let's see. I have a tertiary carbon, a secondary carbon. We know that Markovnikov's rule favors the formation of the more substituted carbocation. So we know the carbocation is going to form there. That means the nucleophile, the chlorine, will add there, and I don't need to draw the mechanism to figure this out. All I have to do is redraw my skeleton, put the nucleophile, the chlorine, right here at the more substituted position, and as a default, as a by the way, the hydrogen adds in at the less substituted position. This reaction follows Markovnikov's rule because it has a carbocation intermediate. And we have not yet discussed syn and anti-addition in context of these reactions because we have a carbocation intermediate, and that means it's not really going for syn or anti. Let me show you why. If I use a ring for this reaction, as I showed you before, and I start with a pi bond, the pi bond breaks, and I now have my carbocation intermediate with a hydrogen that added to one side. Let's randomly put it at the top, put another hydrogen that was already there at the bottom. My incoming chlorine, well, is it going to go towards the top or the bottom? This is where you want to think of the hybridization and the three-dimensionality of this molecule. If I have a carbocation, that is an sp2 hybrid intermediate. And if you think about the geometry of an sp2 hybrid, it's trigonal planar, aka flat. And that means the chlorine can add from the top or the bottom. Therefore, I can get both a chlorine that adds to the same side of hydrogen or the opposite side of hydrogen. And that's why it doesn't matter, meaning we don't get syn or anti-addition. So I'm going to add here no syn or anti with an sp2 carbocation intermediate. So anytime I have the carbocation intermediate, we are not going to be worrying about syn or anti-addition. When we have non-carbocation reactions, we will worry about the syn and anti-addition. If you're with me so far, let me see a couple of hearts in the comments as we move on to the other hydrohalogenation reaction. And this time, we're going to react it with, let's do HBr and peroxides. Peroxides, which you can write as ROOR, or your professors may sometimes give you a very specific one, is going to give me a very different reaction. With peroxides, even though we're not following Markovnikov's rule, the chemistry of why this is happening is going to be for the same exact reason. Let me show you. The intermediate, and I do have a mechanism video on this channel, the intermediate for adding with peroxides is that the radical forms and the radical stability is going to be very similar to carbocation stability. So I want my radical here, but it's not the hydrogen that adds first, it's the halogen that adds first. So after bromine adds at the less substituted position, because the radical can add at the more substituted position, the final step when the hydrogen adds is not because the hydrogen cares about where it's going. It's simply the next step in the reaction is going to give me not a nucleophile in this case because we're dealing with radicals, but it's going to add to the open position. That means we get the hydrogen adding here, the bromine adding here, making this an anti-Markovnikov reaction. But don't just memorize anti-Markovnikov. Recognize the reason it's anti-Markovnikov is because I want to have the most stable, the most substituted radical. And because the halogen adds first, the halogen is going to add to the other position. I haven't learned any of this in lecture yet. Well, this means that you're going to show up to lecture already prepared with advanced knowledge, and hopefully that means you'll have a much easier time understanding it. So I love that you're here before you've even covered it. All right, so we have anti-Markovnikov, and just like the carbocation, the radical can be on the top or the bottom. That means the addition of the last step can happen top or bottom. So that means we're not looking at a syn anti situation. We're just looking at, well, it adds either side. So if, I should point out that if the final product is chiral, it's going to be racemic. So I'm just going to put racemic if chiral, and that means I'm going to get 50-50 R and S because of how it adds. And same thing here, this one is achiral, but if it was chiral, it would be racemic for the same reason, because we had a carbocation intermediate. All right, so let's look at these two reactions one more time. The hydrohalogenation with an inert solvent, this is sometimes called the light reaction. And I'm sorry, this is called the dark reaction. The dark reaction means we don't have to add any light into the situation. And this is sometimes called the light reaction because you can use peroxides or heat or light for radical formation. And so professors will sometimes test you on that dark versus light, radical versus non-radical, to get between these two. The first one is Markovnikov. The second one is anti-Markovnikov. Dark for Markovnikov, light for anti-Markovnikov. What if I change it up though? What if I take my starting molecule and this time, instead of reacting it with HX, I react it with X2, for example, Cl2. In this case, the reaction changes ever so slightly because even though I have the pi electrons reaching out to attack, we get a very interesting intermediate in this case, where one of the chlorine atoms that got attacked winds up grabbing both sides. So what happens is the pi bond grabs the chlorine, and the chlorine then reaches out and grabs back. So chlorine is holding the carbon, carbon is holding the chlorine. You get this very small, very unstable, charged, very, very unhappy situation of a ring. And this is where it gets interesting. The other chlorine, the Cl- that wants to come in and attack, cannot come in from the same side as the chloronium ring, as this tiny little triangle, because it's being blocked. And so if the ring is at the top, the other chlorine has to add from the bottom. Let me show you what that looks like on a cyclic alkene so that you can understand what is happening. If I have an intermediate that looks like this, where the chlorine bridge is on wedges, it's at the top. If another chlorine tries to add from the top, it's blocked. That chlorine, the green one, is in the way. So the only other option here is for that Cl- to sneak in from behind the molecule, from the back, from underneath, for a backside attack. And if it winds up breaking one of the bonds, they go in opposite directions. So let's say we wound up breaking the bottom bond. That means that the green chlorine, which was on a wedge, stays on a wedge, but the blue one had to come in from the bottom. That's not blue. Let's try that again. Here we go. The blue one has to come in from the bottom. And so what we get here is an anti-addition, not anti-Markovnikov, anti as in they're adding to opposite faces of the pi bond. This is our first anti-addition. Not because you're memorizing it, but because I want you to recognize that when they add from opposite sides, that is the definition of anti, adding from the opposite direction. Let me know if that makes sense. Let me know if you feel comfortable with a concept of why it's anti rather than just a memorization. So let's go back to here. And we'll show the shortcut for this is you break the pi bond, you redraw the skeleton. I don't know why that one just disappeared on me. You redraw the skeleton, and then you put one halogen in one direction and the other one in the other direction. In this case, it doesn't matter because this one is chiral, but this one is achiral, given that I have two methyl groups. But in the case of the ring, we definitely have to show opposites, and I could show the first one on top, second one on bottom, or I could have shown it the other way. So I would have gotten the enantiomer as well. I'll just write plus enantiomer, so you know you would have had a second one there. Let's try one more with the halogen. Let's say, in this case, I am back to reacting it with Cl2, but this time, instead of using an inert solvent like CCl4, which is not reactive, I choose to put it into something like H2O, water. This is going to start out the same way, and so my intermediate will have the chloronium bridge. Whoops, my lines are a little bit drunk today. I have the chloronium bridge with a positive charge, and I would expect my other Cl- to try and attack to get in there like before. The problem is, if this is in a solution of water, the water molecules, should have saved the blue for water. Let's change this up a little. We'll make this one purple, and then we'll bring in blue water, is going to completely surround and cage the halogen. My toddler lately is going through this phase where we drop him off at daycare and he decides, I know, go to daycare today. And he will just cling with a, what do you call that? A steel grip. He does not want to let go because he just wants to hold on. That is what is happening to the chlorine atom, to the chloride ion. That chloride is not going anywhere. The water is holding on to it so tightly, so carefully, it's trapped. It cannot react. So what happens to the molecule? Well, it's waiting and waiting and waiting until a water molecule passing by with its lone electrons on oxygen, its electronegative but not negative electrons, realizes that you have a partially positive situation going on there, and then ultimately the water will attack at the more substituted position. The other hydrogen gets deprotonated, and the product looks like this. We redraw the skeleton. The shortcut is you break the pi bond. I meant to do that in red. You break the pi bond. You put the halogen on the less substituted carbon. You put the incoming nucleophile minus one hydrogen atom. So instead of H2O, it's only H1O, an OH like that. And you get what is called a Halohydrin, where halo tells us we have a halogen and hydrin is the OH group from water. So the Halohydrin follows Markovnikov's rule, even though there is no carbocation. And the reason for that is the water, the final product being an alcohol, added at the more substituted carbon. But I told you that Markovnikov's rule has to do with the carbocation. There's no carbocation here. So how does this make sense from Markovnikov's rule? Very simple. Let's take a look at the intermediate one more time, and let's look at it for the ring. So I have this right here. It breaks open, and what I have is a chloronium bridge like this. It's got two lone pairs and a positive charge. Now, chlorine, you should recognize, is a very highly electronegative atom. It does not like a positive charge. So it starts pulling on the pi bond, on the bond between itself and carbon. It starts pulling and pulling that electron density away from carbon, making the carbon holding it very partially positive. Now, if I have a substituent here, for example, I'll throw in a methyl group, this carbon, being more substituted, is capable of holding a much stronger positive charge. And so chlorine is pulling a lot more on that bond, so that carbon is helping hold that burden of charge. That makes this one more partially positive. And according to Markovnikov's rule, that's where the incoming nucleophile attacks. And so even though we don't see a carbocation intermediate, this technically follows Markovnikov's rule. So I'll put Mark's rule. Another thing I want you to recognize here is, let's go back to the ring where you can clearly see it. Because of the chloronium bridge, this intermediate is not isolated. If, let's show, there was a methyl group here. If the chlorine bond breaks on the bottom, the other chlorine is still here with a wedge up and out of the page. The methyl group that is over here gets pushed up. Why does it get pushed up? Because water The incoming nucleophile is coming in from the bottom, pushing the methyl up so that it can attach on the opposite side. And that means the two incoming groups, chlorine and OH, are on opposite sides. That is how we get the anti-addition, even though we never saw a carbocation intermediate. All right, are you with me so far on these reactions? Don't forget, layerforsci.com/orgolive. You'll get all the session notes, everything that I'm drawing today, along with additional alkene reactions practice so that you can try the more advanced problems, because I'm teaching with simple problems, but I want to make sure that you can do exactly what I'm showing you here on even trickier problems, the kind that your professor will try to get you with on your quiz or exam, but you're not going to fall for it. What reaction should we look at next? Ooh, this is a fun one. Okay. One reaction that you're going to see a lot in organic chemistry, because this is going to be a good way to put an alcohol onto a molecule for later synthesis, is acid-catalyzed hydration. Notice how I purposely moved the pi bond over one position, because I want to teach you an additional trick here when we're looking at what is happening. In acid-catalyzed hydration, my acid catalyst will be a strong acid, for example, H2SO4. Anytime you see an acid, H2SO4 is not reactive. It is simply a source of H plus in solution. Ignore the rest. HSO4 minus, not reacting. Even if it's not shown, this is a reaction that takes place in water. It's an aqueous acid that we're using. H plus, very similar to when we're reacting with HX, is an electrophilic addition where the pi bond will use the electrons to grab that proton. And if we follow what I showed you before, you'll recognize that I have, what do I have? I have a secondary carbon and a primary carbon. Where would I put the carbocation? Meaning, what does Markovnikov's rule tell me? The carbocation goes to the more substituted carbon, which would be secondary, except look at what I have on this molecule. If I form a carbocation right over here on the secondary carbon, because my hydrogen wound up at the primary position, I have a secondary carbocation right here sitting next to a tertiary carbon. If I can somehow turn the tertiary carbon into a carbocation, would that not be so much more stable than a secondary carbocation? Yeah, so let's do it. Let's grab that hydrogen atom and move it over together with the electrons. The entire hydrogen end bond move over, giving me a brand new carbocation that had nothing to do with the position of the starting alkene. And that means if I had a hydrogen right here initially, that's still there. Now I have the dark gray hydrogen from the hydride shift, and that blue one that added from the first step, which I showed in red here, but that's the blue one. And let's not forget that I had these two hydrogens here as well. This trick right here, you do not have to draw it unless you're showing the mechanism. Instead, here's what I want you to recognize. Anytime you have a secondary carbocation near a tertiary carbon, you will have a hydride shift, a carbocation rearrangement to give you a more stable carbocation intermediate. And that means the shortcut for this is you redraw the starting molecule, you break your pi bond, you recognize that you have a secondary carbocation near a tertiary carbon. That is where your nucleophile is going to add. And for a nucleophile like this, the backpack trick, which is something I should link here, so I'll put it in the links below. The backpack trick tells us as follows. We cross out one hydrogen and then add the rest. That means I add an OH right there. And that is my final product, an alcohol at a position that never had anything to do with a pi bond, simply because of a carbocation rearrangement. Martin, if you can do me a favor and just translate that to English, I would really appreciate it. My, I think German, I don't understand. My German is not very good. All right, so that is the first reaction to put alcohol onto the carbon chain. This reaction, because of a carbocation intermediate, follows Markovnikov's rule. And because we have a carbocation intermediate, it is not going to do syn or anti-addition because the carbocation is able to add from the top or the bottom. It's sp2 hybridized, it's flat. But if my product was chiral, it would be racemic. In this case, it's not. But if it is, you do want to keep in mind racemic if chiral, because you can add to the top and to the bottom. So one of them would give you R and the other one would give you S. What if I don't want to have a carbocation rearrangement? What if I want my alcohol specifically at carbon, at the primary or the secondary carbon? I'm going to have to use a different reaction to put the alcohol on there. And luckily, I know of quite a few. So let's take a look at oxymercuration. And this is oxymercuration-reduction because the last step is a reduction, or the second half of the reaction is a reduction reaction. We'll start out with the same alkene with the pi bond all the way at the end. And the mechanism is kind of lengthy. I do cover it in a separate video. Where step one, I'm going to react with HgOAC2 in a solution of water. And step two, for the reduction, I'm using a reducing agent, NaBH4. Hydrogen, that's your clue that it's a reducing agent. Very similar to the halogen when we did the halogenation reaction. The intermediate for this is going to have a mercury or mercurium bridge where the Hg is holding on to both sides. It still has one of the OAC groups and it's got the positive charge. So just like we saw with a Halohydrin formation where we had no carbocation, but we still had that positive that directed the incoming group, this is going to get the nucleophile ultimately coming here at the more substituted. But because we have no carbocation, we have no carbocation rearrangement. And that's why I call the mercury reaction, I call it the carbocation babysitter. This is the reaction you use if you want to follow Markovnikov's rule, but you want to make sure the carbocation cannot move, it cannot rearrange. And the shortcut then for coming up with a product is very simple. As before, you break the pi bond, you identify that this is a secondary carbon, this is primary. Secondary is more substituted for Markovnikov's rule, but no rearrangement. And so the alcohol, following the backpack trick, notice we have a molecule of water. We cross out the hydrogen atom, and this right here, that's my alcohol, is going to add at the more substituted position. And then the hydrogen, following Markovnikov's rule to the less substituted side, goes on the primary carbon. This reaction, we already explained how it follows Markovnikov's rule, even though it does not have a carbocation rearrangement. But there's also something else very interesting. This is considered an anti-addition. So let me show you why this is an anti-addition. The last time we saw a bridge like this was a halogen. And remember I said with a halogen, if the bridge is at the top, the incoming nucleophile has to come from the bottom. The same exact thing is happening here because look at that, we have a bridge. And so if I showed you this reaction with a ring where you're very clearly able to see what is happening, and I'm going to react this with HgOAC2, H2O, that's step one. Step two is NaBH4. Then my product is going to have the pi bond. Once again, we show the pi bond breaking. In this case, it doesn't matter where I put the alcohol because I don't have one more substituted than the other. I have symmetry in the molecule. And so if I choose to put the alcohol on a wedge on top, I have to put the hydrogen on dashes. That's not a hydrogen. On dashes at the bottom because it's an anti-addition because of that bridge. Now, the steps are a lot more complicated than halogenation. So if you want to see the mechanism, go find my video for that on this channel. But the shortcut here is just recognizing the bridge forces OH on one side, H on the other side for an anti-addition that happens to follow Markovnikov's rule. If I want to find a way to put the alcohol on the primary carbon, something that's going to be very important for later reactions, then I'm going to use the third reaction in my toolbox, and that is hydroboration. For hydroboration, this is followed by an oxidation reaction. I will start out with the same alkene, and this time I'm going to react it again with two steps. Step one is BH3 in THF, that's my solvent. And step two is NaOH, H2O2. Some professors also want you to put water. BH3 is not the only thing you can see. You'll see a couple of different versions of it. So as long as you recognize the boron, that's the B. Kind of missed there. That's the B in hydroboration. So any version of this boron reagent is going to give you the hydroboration. This reaction is very interesting because we have a concerted mechanism, and I do cover this mechanism in a separate video on this channel. I'm going to show you the part that matters. The molecule will line up where the boron sits towards the end, the hydrogen sits here, and the rest of the molecule hangs off. I say the rest of the molecule because boron will attack 1, replace the hydrogen, attack 2, replace the hydrogen, attack 3. So let's assume that it's already attacked 2. It's got a long R group here and a long R group here. The R group has to hang over the side of the molecule. It can't go here because it's going to crash in here. And so the hydrogen, you'll notice, lines up with the more substituted part of this molecule. Boron lines up with the less substituted. And that's where you have this getting attached and this getting attached. When that happens, the intermediate, and that's actually what I was trying to show here, so I'm just going to turn this into the intermediate, you get something wonky that looks like this. Both hydrogen and boron are attached. This ultimately breaks off. And note, why is that not erasing? And now notice that hydrogen wound up on the on the more substituted carbon, most definitely not following Markovnikov's rule. So this is an anti-Markovnikov reaction. But to make matters confusing, because they added at the same time, did you see how they both kind of got stuck at the same position together? They are adding to the same face of the molecule, making this a syn addition. They add to the same face, but the OH ultimately gets to the less substituted carbon. The shortcut for this reaction, we break the pi bond, redraw the skeleton exactly as you see it, put your alcohol on the less substituted carbon and hydrogen on the more substituted carbon. No carbocation, no rearrangement. If I want to see this on a ring, and let's make this a substituted ring so that you can really see what's going on, we'll react it with BH3, THF. That is step 1. And step 2, we have NaOH, H2O2. We break the pi bond. We redraw the skeleton exactly as we see it, but this is where it changes a little bit. The alcohol goes to the less substituted carbon. So this time I'm going to let's show this in a different color so it stands out. Alcohol goes to the less substituted carbon. I'm showing it going down. That means the hydrogen also has to go down, and therefore the methyl group that was already here got pushed up. So that right here is my CH3. That is one option. Or I could have done it the exact opposite way, where the alcohol came up on a wedge. That means the hydrogen also came up on a wedge, and the methyl group had to go down on dashes. Less substituted carbon, anti-Markovnikov. Same face of the ring, both going down or both going up, and that's what makes it a syn addition. Oh, wow, we're almost at the hour. So let's see how much time we still have, because there's a couple more reactions. Actually, I want to show you something. I want to show you all three together, because this is going to be so important for synthesis. One alkene, one alcohol, three different products. So let's see how that's possible. 1, 2, and 3. Let's draw the skeleton 3 times. If you have a starting molecule like this, with potential for a carbocation rearrangement, and your professor asks you to put the alcohol on any of the 3 positions, here's what you want to consider. If you're using an acid-catalyzed hydration like H2SO4 and H2O, carbocation rearrangement, the alcohol goes to the most substituted carbon, even though the pi bond was never there. If you want a Markovnikov product with no rearrangement, that's where you're going to use oxymercuration. H2, H2O, step 1. Step 2 is NaBH4. And if you want the alcohol on the least substituted position, you put it all the way at the end. This is going to be your hydroboration, BH3 in THF, step 2, NaOH, H2O2. Some professors want to see H2O. This right here, I had learned the individual reactions, but in putting them together like this, wow, right? Same starting molecule, same functional group, 3 different positions. You just opened up such a good arsenal for when you're looking at the advanced reactions, because you can say, I have an alcohol, I want to put whatever else there. I can use that alcohol to turn it into something else, but I have so much control over what is going on. For even more practice, especially advanced, tricky questions, because my quiz is not this easy. I give you all the easy problems here. Go to leahforsyth.com/orgolive. You'll get a copy of all the notes from today's session, as well as the Alkene Reactions Practice Quiz. If you're looking for even more, including the step-by-step where I show you every single practice problem on the quiz and actually break it down for you. This is the question. Here's how we approach it. Here's what we're looking at. Kind of like I showed you today, but for all the advanced problems, come join me in the Organic Chemistry Study Hall. For just the topic of alkene reactions, I cover all of the reactions, practice, more practice. I show you how to break down the quiz. There's a session on the stereochemistry of alkene reactions and so much more, not to mention every other topic that you need to know for Organic Chemistry 1 and Organic Chemistry 2. The link is leahforsyth.com/join.